Not bending. Oh, I see it.
Oh, it's bending.
All right.
Oh, wow. That's
A little bit. So, all right. So, a few of the problems. Let's take a look at a few of these, and then I'll make sure all the rest of the answers are down, so you'll be able to check them. But running a product rule on number 4, I have two different versions of that answer written down. The first version is where I've just cleaned it up a little bit. One of the things that you'll see most often is ultimately when you end up with a trig function times a polynomial term, usually they'll rewrite it with the polynomial term piece in the front. So sine of x times 2x, 2x times sine of x is the more common way to write that. It definitely can become confusing, especially because when you see this, you may think, oh, x times 2x is 2x squared, but that x is part of that sign. You cannot change that x by multiplying by something on the outside. So a sine of x, kind of protected, x is part of that sine function, 2x can't affect that. 2x sine x would be the appropriate way to write that. X squared times cosine x. This is me showing, and we should always, we could be able to see that, g, f prime, f, and g prime. You won't see me list those out over on the side every time, but you can absolutely do that, and that is, go over to f is x squared, so f prime is 2x, and g is sine, so g prime is cosine, and then put the pieces into your product rule. You may see this answer with an x factored out. You don't have to factor an x out of both, but you could. Some of this is about looking at how the answers are presented to choose from. You may have to look for an answer where something has been factored or something else has been simplified. So I kind of always recommend sort of looking at the answers at the same time that you're sort of, as you're working through the problem, sort of like, okay, here are my answer choices. Gives me an idea of kind of how far I'm supposed to be going for simplifying. Yes?
Do we have to put the y equals 2?
You should put that. Yeah, you should absolutely put that. And that's, yeah, you should really put that. All right. So if y is x squared sine x, then y prime, or dy dx, the derivative of that with respect to x, is equal to that. Yeah, good call. Quotient rule on number 5. Once again, nothing, I think we talked about this one real quick before lunch. Nothing, we can't divide any of these out. We can't take that common factor here and here because there's not a common factor that matches that here. Writing sine x quantity squared or writing it as sine squared x, that's just a preference. This is the more commonly presented notation, so I want to make sure you see it. But that is my preference on how to write it. And then, I'll get your question in a second. On number 6, cosine times cosine plus sine times negative sine. That's going to become cosine squared minus sine squared, which actually is an identity. And so you may or may not remember that one. But that is the same as cosine 2x. That's the double angle, one of the double angle forms for cosine. So that's another possible answer. Okay. Question?
Oh, number 5.
Uh-huh.
Could you write it as for the cosine part? Could you write it as cosine x squared?
No. And I'm glad that you asked that. Because when you take x times cosine x, those are two separate things. It's kind of like taking x times the square root of x. You can't just kind of jam this x in there with that x without things changing. When you have something like the sine of x, when I multiply that by something, that's the sine takes precedent. It's not x times the x and then taking the sine. Okay. So no, and I'm really glad you said that. So x cosine x has to, or you could write cosine x and then times x after it, but that is a little awkward because then that starts to look like cosine of x squared. That's why we typically write the polynomial term first. And did I do that? G f prime? No, and that's naturally what happens in this one. Okay, just thinking. Okay, I want to go ahead and do a tangent line problem. So let's go down here to the bottom. And then I want to talk about some of the second derivative stuff on the back, do a couple of those, and then we'll be ready to go. So, like I said before, tangent lines, we're going to write equations of tangent lines over and over and over and over again. A normal line is just the line that is perpendicular. Oops, except I'm not spelling perpendicular correctly. Perpendicular to a tangent line. So from geometry, lines that are perpendicular, the slope of the normal line is going to be equal to the opposite reciprocal of the tangent line slope. Opposite reciprocals, lines that are perpendicular, have slopes that are opposite reciprocals. The product of the slopes of perpendicular lines is -1. So if, for example, we did a tangent line problem and let's say the tangent line had a slope of 2/3, then writing the normal line, everything else would be the same except I'd use the same point, but I'd be using a slope of -3/2. Okay? I think you actually run into that question or talks about a normal line, and it does say what it is in one of the homework problems. This is a little bit of an easier problem though, so let's do this one. Okay. Fine, let's just do the tangent line of this function at x equals pi/3. Okay. So what do I need to write the equation of a line? I need a point. All right. So let's start with a point. I know x is pi/3. Cool. F of pi/3 will be my y. So that's going to be -3 sine of pi/3 tangent of pi/3. So to get my point, I have the x given. I find the y by plugging the x into the original function, the function that we're making the tangent line towards. Okay. Pi/3, 60-degree family. I still think degrees sometimes. 60-degree family. So 60 degrees, or pi/3, up higher up on the unit circle. So, everybody sort of has their own different ways to think about memorizing things regarding the unit circle. For me, for pi/3, I know it's up there. So I know it's going to be the little x and the big y. I know the ordered pair then is 1/2 √3/2 because that's the little x. 1/2 is smaller than square root of 3/2. So sine of pi over 3 is root 3 over 2. And if we're not remembering our tangent values, tangent of pi over 3 would be the sine of pi over 3 over the cosine of pi over 3. So pi over 3 over 2 over a half is root 3. If this question is sort of getting you where you're like, ooh, yeah, oh, unit circle stuff, and pi, sines and cosines and tangents of unit circle family values, then yeah, that's something you need to be worrying about, because when we see, anytime we have trig, chances are we're going to be plugging things into those trig functions. Like you did on your test, where you were doing that limit problem with the sine and the cosine squared of pi over 4. So this is going to be negative 3 times 3 over 2, negative 9/2. So right now, I know part of my line, y plus 9/2 equals something times x minus pi over 3. Unfortunately, that's not a calculus question yet. This is no calculus. There's been no calculus that has happened yet. All we have done is plug the pi over 3 into that function and evaluated it, and then started to build the point slope form. What else do we need? We need a slope. That's what's going to go right here. We need the slope. My function is negative 3 times the sine of x times the tangent of x. Where do I get the slope? Where do I get the slope of a tangent line? Take a derivative, right? So we need y prime, the y prime function, or the derivative function, to give us our slopes. This is a product. So as I write my derivative, I am going to have to follow the product rule. It always feels a little scary when you it's sort of like 3 pieces in that product. You're like, oh, 3 pieces. Remember, you don't have to consider constants as a product rule set piece. You can kind of just tag that negative 3 with a sign. So I'm looking at this as a one function. This is the second function inside the product. Okay, build me a product rule derivative out of that negative 3 sine x times tangent x. G. Okay. So G, F prime.
I just wasn't making the connection in my head.
Yeah, it's okay. F.
I'm gonna do
If you see me using these parentheses, it's because you want to be really careful. You are multiplying these two pieces. And when you take a tangent times a negative 3 cosine, if you don't have the grouping symbols, you may start to look at this as a subtraction problem and not this times this. Also, the other thing that's kind of important or good to talk about here with something like this, I don't have to make this look pretty before I plug in pi over 3. Actually doing that is sort of a waste of time. So I don't really care how messy and ugly this looks. As long as I have done the product rule correctly, I am ready right now to throw my pi over 3 in there. I don't have to pretty it up first before I substitute. Prettying it up and then substituting in this problem is a waste of time, because no one's going to look at the pretty part. We're only going to ultimately look at, did you do the product rule? And then where did you end up? With what value did you end up for the derivative? So, three.
I mean, like, we don't have to try to back that, yeah, but it's just the house
This is so much fun. Okay. Okay. So here's another thing I noticed, and I saw this on your test. A lot of you, when you had the cosine squared part, it's like you thought you were going to have to square the angle and then take the cosine. Like you were going to, like that this would mean to square the pi over 3 and then take the secant. It's the secant value squared. A number is going to go in here that is the secant of pi over 3. And then I'm going to square that number. That's how an exponent works on a trig function. The trig function happens before the exponent, because essentially there's, if you want to hit it with like, please excuse my dear Aunt Sally, the trig function is in parentheses, bless you, and then the exponent is attached to that. That is the intent. Even though it doesn't look that way when we write it with this kind of gross notation, that's the meaning. It's the secant of x quantity squared. Okay. So let's see. Secant is reciprocal of cosine, and cosine is a half because it's the little number, it's the x, and so secant is 2. So 3 over 2 plus, I'm just going to go ahead, 4.
I really thought it was like that, bro. I was trying to hit it with my
Yep. Four.
That would be 4.
No, I'm making something. Oh, no, I was right. Okay. Check it out right here. Yeah, that's right. Okay. So, when I start putting this together, once again, here we are back with our arithmetic struggles. Root 3 times negative 3 over 2 is root 3 over 1. Okay. And so that's negative 3 root 3 over 2. When I went over here, 2 squared is 4. 4 times negative 3 is negative 12. I thought about reducing, but then I was like, well, wait, this has a 2 denominator. So how about I'll leave that 2 denominator? I won't do extra reducing. So 4 times negative 3 times root 3, negative 12 root 3 over 2. If I rewrote this as negative 6 root 3, I then would have had to go back and think about the negative 6 plus the negative 3 over 2 in terms of root 3. Also, I'm adding 2 expressions that have the same rational piece in them. My answer has that same rational piece. Now, why were we doing all this? What was this? This is a slope. Yeah, this is supposed to be the slope on a line that looked like this. If we went, if I go back up and go, okay, what was the x was pi over 3, the y was negative 9 halves, and so y plus 9 halves equals negative 15 root 3 over 2 times x minus pi over 3. And I'm going to continually make a plea for you to practice and do problems that I've given you to practice, because you can see right here, if this is considered I don't know, it's not an easy problem, but this is not really a difficult problem in that when I tell you to write the equation of a tangent line, there's a set of steps to go through. It's not confusing as to what you're supposed to do. Every tangent line problem is essentially the same. Find the point, find the slope, make the line. It is a little challenging because of the derivatives. You have to do product rule, you're using your trig derivatives, and you're using trig values. That would make this problem more difficult. But all of those things are not, some of those things are not the calculus parts that are difficult. The calculus in this problem is not supposed to be a big issue, and the trig is not supposed to be any issue. And if you don't feel that way, which I'm sure like, oh, I don't feel that way, that's why you gotta practice. Okay? Yeah, do your practice like I've been telling you. All right, so